In this video, I'm going to try and explain why we don't tend to talk about the grain size when we're talking about microwave and radar scattering in snow, and why we use something called the correlation length as a more useful statistic for the microstructure of the snow. When I started learning about snow, I imagined it was like a ball pit where it was essentially a pile of snowflakes, and I imagined those snowflakes as round, and I also imagined that when you took a cross section through the snow, it would look a bit like this. It would look like lots of spherical balls, all clustered together in a pile like a ball pit, and you could maybe measure the diameter of the spheres, average them, and you could say the mean grain size is 1 millimeter plus or minus 0.2 millimeters because there's a distribution of sphere sizes in there. But it turns out if you actually take a cross section of real snow, it looks like this. It looks quite different, and intuitively it's not obvious how to characterize the grain size by eye there. You can't just like average some lengths and see what you get. So we need a bit more of a nuanced tactic to characterize the size of to characterize the length scale of that snow. So let's zoom in on the snow microstructure itself from the last slide and just draw a line through it. And any old line will do. We'll draw a horizontal line. And we're going to look at that line and we're going to make a function. And I should add that for this picture, it's white where there's ice and it's black where there's a void space. So our function is going to have the value 1 when there's ice, and it's going to have the value 0 where the line is in void space. So that function looks like this. It looks like a barcode. And to think about the microstructural characteristics of the snow, we're going to take the autocorrelation of this barcode function. And what that means is we're going to look at the function, and then we're going to shift it by a certain amount along the x-axis, and we're going to see how well correlated it is with the original function. So I'm going to illustrate that now. We're going to shift this function by 1 unit to the right. We're going to turn it orange, and we're going to look at the overlap. So there's quite a lot to take in on this slide, but the top row, I've shifted the original black function by 1 unit, and I've turned it orange. And there's quite a lot of overlap. So most of the bars of the barcode are almost completely overlapping with the orange function because I've only shifted it by 1. And on the bottom row, I've explicitly drawn the overlap, and you can see that the overlap looks almost exactly like the original function because we've barely shifted the top function by anything. So the green function, if you took the area of it, it would be almost exactly the same as the original function. It would only be a bit smaller. But what happens if we start to shift it by a bit more? So here's x equals 2. You can see immediately that the total overlap is reduced significantly. And that means the correlation between the two functions on the top row is also reduced significantly. And hopefully you can extrapolate this in your mind, that as you shift the original function by more and more, the amount of overlap goes down and the correlation between the original function and the shifted function goes down more and more. And you can do that over a continuous range, and that is called the autocorrelation function, or sometimes just called the correlation function. And that's what you can see on the right here. So if you drew a lot of lines and did this a lot of times, you end up with a pretty smooth function that describes the way that the snow microstructure decorrelates as you shift it more and more. And to squeeze just one number out of this correlation function, we look at how far you have to shift before the correlation drops below 1 over e of its original value. And that's, to a large degree, an arbitrary amount, an arbitrary threshold. So I've illustrated it on the right. For this, it's 1 millimeter. So this snow that you can see on the left from Reber et al. has a exponential correlation length of 1 millimeter. And I say exponential correlation length because it's still a topic of quite active research, what this function actually is on the right, what we should best fit to this curve. But an exponential decay is pretty popular. So that is what the correlation length is. It's how far you have to shift that original top function before it decorrelates with itself. And you can see that where there's larger bits of ice, you have to shift it a lot further to decorrelate it. So the correlation length gives us an indication of the typical length scale of the ice microstructure in the snow.